All right, so this is, what is this, part three? Part three, right? Part three. Part three is section 17.4. Hopefully this will be the last one because this is the last one. Okay. We are in the Lagrange multiplier section, so our job is to maximize a function subject to a constraint, some sort of limitation. All right, so here we go. A manufacturer estimates that its total production of car batteries measured in thousands of units is this function right here. X represents the number of units of labor. Y represents the numbers of capital. Labor costs are $160 per unit. Capital costs are $300 per unit. How will production be maximized? So we want production to be maximized if the firm has $80,000 to spend. All right, so I read the problem and I noticed that something's missing. In all the other problems, they pretty much gave me a bunch of stuff, but okay. I'm not sure where the constraint is. I think this is the constraint right here, that I only have $80,000 to spend, and somehow I need to use this to make some sort of a function that's going to be that constraint. So what does it look like? Well, it looks like the money I spent has to be $80,000. So the $160 for every unit of labor plus the $300 for every unit of capital must work out to be $80,000. And then that's going to be my constraint equation. Right? All right, if that's my constraint equation, then my function g of xy will be equal to 160x plus 300y minus 80,000. Well, that looks good. All right, so I've got my objective function, the function I want to maximize in this case. I've got my constraint function, my g of xy. So now I can take those two things and build my Lagrange function. So my Lagrange function, f of x, y, lambda, is going to be equal to f of xy, 3x to the 1/3, y to the 2/3, minus lambda times 160x plus 300y minus 80,000. And then I'll distribute that negative into there, and that's going to give me 3x to the 1/3, y to the 2/3 minus 160 lambda x minus 300 lambda y plus 80,000 lambda. Now that I've got my Lagrange function, next step is to find those first partials. So the first partial with respect to x, oh boy, okay. So the first partial with respect to x, the derivative of that first term with respect to x is going to have a 3 times 1/3 x to the negative 2/3 y to the 2/3 minus 160 lambda. Now I'm going to clean that up a little bit because that 3 and that 1/3 are going to cancel each other, and that negative exponent really means that goes into the denominator. So I'm going to see that as y to the 2/3 divided by x to the 2/3 minus 160 lambda. Okay. All right, let's find the other ones. F sub y, the first order partial derivative with respect to y. Let's see, that's going to be 3x to the 1/3. Actually, you know what? I should change colors because I finished up the last one in light blue. I should do this one in a different color so it stands out. So orange. So f sub y, the first partial derivative, is going to be 3x to the 1/3 times 2/3 y to the negative 1/3 minus 300 lambda. Now I'm going to clean that one up. The 3 and the 2/3 are going to cancel, give me 2, and that negative exponent really means downstairs. So that's going to give me 2x to the 1/3 divided by y to the 1/3 minus 300 lambda. Right. Now I'll find f sub lambda. First term goes away. The second term is negative 160x minus 300y plus 80,000. And then I'll check to make sure that that works right. Is this, oops, undo that. Is this the opposite of our g of x function? And it is, so I feel good about that. And now I'll start trying to do some algebra here to set these equal to 0 and solve. Well, what has worked every single time in the past, I'm just going to redo. If this is equal to 0, then I'll just solve for lambda. That gives me 160 lambda is equal to y to the 2/3 over x to the 2/3, or lambda equals y to the 2/3 over 160 x to the 2/3. Okay. Same logic here. 300 lambda is equal to 2x to the 1/3 over y to the 1/3. Divide by 300, I'm going to get then that lambda is equal to x to the 1/3 over 150 y to the 1/3. Right. Now I will set lambda equal to lambda, or y to the 2/3 over 160 x to the 2/3 is equal to x to the 1/3 over 150 y to the 1/3. Cross multiply. Oop. And that's going to turn into, let's see, 160x is equal to 150y. Or the x is equal to 15/16 y. Well, that worked out really, really nice. It's almost like whoever made this problem up made it to work out nice. All right, so what do I do with this? Oh, every other time, I would take that and substitute it in there. And so that's what I'm going to do. So let's see. Negative 160 times x, but x is 15/16 y, minus 300y plus 80 grand is equal to 0. Let's see, so negative 150y minus 300y is equal to negative 80,000. So y is equal to 80,000 divided by 450. I'm going to grab the calculator. What's 80,000 divided by 450? Darn it. I'll make it into a fraction. 1,600 over 9. Okay. And then I'll use this to find x. So then x is equal to 15/16 times 1,600 over y. Oh, one too many zeros. It is 1,600, right? Yeah. The 16s will cancel, and that just gives me what? Why did I write y? It's 1,600 over 9. And so the 16s cancel, and I get 1,500 over 9. Those both divide by 3, so 500 over 3. Okay, I've got the same problem that I had a long time ago in the first example, where I only have one point, so I need to make up a second point to compare it to. So where's my constraint? My constraint's right here. So what if I let y equal 0, then what would x be? Well, x would be that 80,000 divided by 160. And what's 80,000 divided by 160? Be 500. So there's my comparing point. right, so my solved for or found point was the point x equals 500 over 3, y equals 1600 over 9. The point that I'm going to compare it to was x equals 500, y equals 0. And I compare them by putting them back into the original function f. And so f of xy, my production function, was it 3x to the 1/3, y to the 2/3? Yeah. 3x to the 1/3, y to the 2/3. So 3 times 500 over 3 to the 1/3 times 1600 over 9 to the 2/3, and that's going to be equal to a calculator problem. So 3 parentheses 500 divided by 3, close parentheses raised to the 1 divided by 3, times parentheses 1600 divided by 9 raised to the 2/3, and I get 521.98. Now I'll do the same thing over here for my compare point. F of 500, 0 is going to be, it's just going to be 0 because of that y term right there. All right, so that's bigger. So I know that I found a maximum. So the maximum production is 521.98, and I'd round it wherever they tell me to round it, when x is equal to 500 divided by 3 and y is equal to 1600 divided by 9. Now, there is one small problem with this. I go back up here to the stem of this problem. I'm not certain if this is going to be allowed to be a fractional number and this is going to be allowed to be a fractional number. Can I have a fractional unit of labor? Because clearly my final answer has fractional units in it. Now, there's nothing in the problem that told me it can't be, but in the real world, this might end up being an issue. And you might have to say, okay, well, 500 divided by 3 is one, so this might have to be rounded to like a 166 or a 167. I'm not sure which, but you'd have to make sure that when you rounded both of those values, that by rounding them, you didn't violate your constraint. Meaning that if I round this one up and I round this one up, it might actually violate that $80,000 that I have to spend. So you have to be careful when you round that you don't violate your constraints. All right. That brings us to the end of section 17.4. It also brings us to the end of chapter 17. So with this video, we effectively close out the hardest chapter in the entire textbook. Well, the hardest chapter in this course, in this textbook. So hopefully everything's going okay for you. Again, as always, if you have any questions, please reach out. Have a good one.